Good afternoon, students. We are going to talk about the mechanical properties of solids. So, by mechanical properties, what we mean is that we are going to talk about the deformations of solids, and we are going to talk about the stretching and bending of solids. So, in the previous chapters, you have learned rigid bodies, and rigid bodies are defined as the ones which have their interparticle distances which remain constant throughout the course of motion. However, that does not stop bending or stretching or extension or even other kinds of deformation of the body. Now, these deformations can be brought about by the application of forces, and even the steel rod, which is known to be quite strong, can be deformed if the applied force is very large. And we are going to talk about two kinds of deformation mainly, one in which the body actually regains its normal configuration once the force is removed, and one in which they do not regain the normal configuration. Mainly we are going to constrain our discussion on the forces which after which if it is removed, the body is going to will regain its normal configuration. So, these are temporary deformations, and mostly we are going to talk about these temporary deformations. All right. So, let us take an example of bungee jumping. Have you heard of bungee jumping? If you haven't, then you might as well want to look at a video in YouTube about bungee jumping, in which what happens is that a diver or a jumper, he or she binds himself or herself along with a extensible cord, and then take a dive from a very high distance or large distance. And this is typically of the order of maybe even a few hundred feet to even more than that. This could be a dangerous act, so please do not try without adequate supervision by professionals. We are not going to talk about the problems that it could bring if a body suddenly jumps from a few thousand feet to the ground because of the pressure difference. Rather, we are going to concentrate on the amount of or rather the material which the bungee cord is made of, and the bungee cord is made up of a material which has a great deal of elasticity. In this video, the boy is seen to give a bungee jump. So, he falls off from a large height. He is tied with a rope. So, so what happens is that as the diver or the jumper jumps from a height, the bungee cord, which is elastic, it keeps getting elongated more and more till it reaches a point which is its maximum elongation, and then the diver comes to a temporary halt, and after that he is going to swing in an oscillatory manner, and this is what makes all this bungee jumping very spectacular. So, so after this initial fall, the jumper actually comes to a momentary halt, and then the cord, as I told, that the cord is stretched to its maximum, and then there is an oscillatory motion that is going to take over, but this oscillatory motion does not carry on forever, and viscous drag due to air and other wind etc. would take over, and then finally the jumper comes to a complete halt. So, this is so this bungee cord is made up of a material which has got this intrinsic property of getting extended because of this force, or which is basically here the weight of the jumper, and then the cord is going to regain its original shape, and that is why the oscillatory motion occurs. So, it is from this discussion of this bungee jumping, it is clear that it is a property of the body by which it tries to regain its original shape and size after the applied force is removed, and this is called as an elastic material. So, what could be the examples of elastic material? Such as we have a rubber band, there could be a spring which is an elastic material. However, there are examples of materials which are not elastic materials, which means that they do not come back to their original shape and size after the force is removed, such as clay or a dough of wheat, and they are called as plastic materials. So, what actually goes on inside the material for which some of these materials actually regain their original shape and some of them do not? To understand that, let us understand the intrinsic building block of these materials. And by building block, what we mean are the atoms and the molecules and the way they are bound to each other. It will be very preliminary to say that we could think of these elastic materials to be made of springs, okay, where the two balls at the end that you see actually represent maybe atoms or molecules, and the spring like thing that I have drawn here are the connection between them, and when a pressure is exerted on these materials either this way or even these ways, they tend to regain their original configuration. So, so having understood the atomic configurations which really render these elastic properties, let us try to understand that the relationship between the forces, the elongations, and there are terms such as tensile stress and tensile strain that we will come to very soon, and what are their interrelationships between them, and how do we actually quantify some relations by which elasticity can be understood better. So, let us take about an example of two rods, okay, and consider three different cases in which they have same initial length, but different extension. And to make matters even clear, let us call L0 as the initial length, delta L extension. So, case number 2, where we have same initial length, which is L0, but different cross sectional area. And in the third case, we have different initial length but same extension. So, let us draw these three cases one after another. Let us consider these two rods which have these are the unstretched lengths and the areas of cross section are also same area of cross section. Same extension here, same area of cross section again for the third case. So, the unstretched lengths are same. Now, if I cause an extension and apply a larger force F1 here and a smaller force F2 here, I will have more extension in this rod than a smaller extension in this rod. Okay? So, where my F1 is greater than F2. So, this is case 1. Let me draw the same picture to understand the area of cross section. So, I have a rod like this and I have a rod like this which have same L0. However, the cross sectional area is A1 for this and a cross sectional area is A2 for this. So, to create the same extension as is pointed out in point number 2, I am going to apply a much, so the force required to create the same extension in the bigger rod is more in the rod with a bigger cross sectional area. So, here we have F2 is greater than F1 to create the same extension. Going to the third case, we have different initial lengths. Now, to have same extension, I need bigger force in this the rod with smaller length than smaller force for the rod with bigger length. So, this is your L01 and this is your L02. So, my F1 is greater than F2. So, from these three figures, it is apparent that my force required to create an extension L in a rod of length, initial length L0 of cross sectional area A is F is proportional to delta L, F is proportional to 1 over L0 and F is proportional to the area of cross section. So, if we combine all three of them, we can write that F is proportional to delta L 1 over L0 and A. So, I can write it a little more compact by taking this, and so my F is proportional to now delta L over L 0 multiplied by the area of cross section. Now, delta L by L 0 can be called as the fractional change in length. Let us write delta L by L 0 as the fractional change in length, and hence, so I can write or change this constant, I can change this proportionality using a proportionality constant, which can now be told as y, which is equal to delta L by L 0 into A, and this is a very important equation in this study of mechanical properties of solid, or rather the elastic properties of solid, in which it says that the force required to create an extension delta L for a material of length L 0 and cross sectional area A is written as this, where y is known as Young's modulus this Young's modulus is named after Thomas Young, 1773 to 1829. And this formula is going to be revisited a number of times in our discussion, or some variant of this formula will be revisited a number of times in our discussion of elastic properties of solids. So, we shall make this ongoing discussion more understandable, in the sense that let us take the example of a spring. So, the spring is tied at one end and it has an unstretched length L 0, and it is acted upon by a force F, and it undergoes an extension which we denote by delta L. So, this is still L 0, and this is under the application of the force. It undergoes an extension delta L. If we double the force, the extension will be doubled, which means that the extension delta L is proportional to the force applied on the spring. If we triple the force, the extension is going to be tripled. Now, take another example in which there are two springs which are acted upon by a force F. Each will have, assuming that their unstretched lengths are same, they extend by the same amount for each one of them, which is delta L, which we can show it in a different. So, this is delta L, and again, so this is delta L in the application, under the application of this force F. So, which means that your delta L, the extension, is proportional to the original length L 0. So, as we double the length of the spring under the application of the same force, the extension or the elongation becomes twice as much. So, delta L is proportional to L 0, and we have also got delta L is proportional to F. Now, to get the third dependence, that is the dependence on the area of cross section, we need to talk about a wire. So, let us take a wire of a finite cross section, and now take an identical wire of an identical cross section and length, and suppose you apply a force here
This is equivalent to the fact that there is a larger area of cross section, same length, and is acted upon by a force F. So, this has an area of cross section A, this has an area of cross section A, this has an area of cross section 2A. So, under the application of this force F, the extension will be delta L by 2, which means as we double the area of cross section, the elongation goes down by a factor of 2. Similarly, if you take 3 such wires, put them together and apply a force F, and then consider an equivalent wire with a radius or rather an area of cross section to be 3A, then the extension is going to be delta L by 3, which tells that delta L is inversely proportional to A, and hence all these 3 relations put together, we can claim that delta L is proportional to F, is proportional to L0, is inversely proportional to A, and again as said earlier, the proportionality constant is called as the Young's modulus, and we can write down this very familiar form, which is y equal to F by A and delta L by L0. So, with the help of this spring, we can understand the dependencies of this elongation on the force, the unstretched length L0 and the area of cross section of the wire, and we can again rederive this same formula that we have derived earlier. Y is called as a Young's modulus. So, let us just come to this discussion of tensile stress that we had briefly spoken about, but hasn't elaborated on it. If I simply divide both sides by A, the area of cross section of the material, the rod in our case, then we will get it as, and Y can simply be written as F over A divided by delta L over L0, and as we have said that Y is called as the Young's modulus. So, the Young's modulus is defined as the tensile stress divided by the tensile strain So, the tensile stress is defined as the force per unit area that is given to the rod of cross sectional area A, and delta L by L0 is a fractional change in length that has occurred because of this tensile stress being given, and Y simply appears as the ratio of the tensile stress and tensile strain. And so, we may want to know that what are the values of this Young's modulus for most materials. For solids it is very high. To quote a few representative values, we can write that we can prepare a table which you will get it in your book, the value of Y. So, for materials such as aluminum, this is 6.9 into 10 to the power 10. And just to point out what could be the dimension of this F over A, which is Newton per meter square in SI unit, whereas delta L by L0 is dimensionless.
So, this will simply have the dimension of the tensile stress, which is simply a Newton per meter square. And for copper, it is slightly over 10 to the power 11 Newton per meter square. Similarly, for steel, which is known to be quite strong, this is of the order. So, this has a value which is 10 to the power 11 Newton per 2 into 10 to the power 11 Newton per meter square, whereas nylon, which is known to be elastic, is 3.7 into 10 to the power 9, which has a value which is less than any of these other metallic items that are quoted here, and a brass has something intermediate, which is 9 into 10 to the power 9 Newton per meter square. So, this shows an interesting fact that steel, which has among these has the maximum value for the Young's modulus, which is 2 into 10 to the power 11 Newton per meter square, simply tells us that the force required, or the tensile stress required to create the same elongation is maximum in steel as compared to any of the other materials that are presented below here. So, let us take a very practical example of where do we get this stress and what are their relevances in our daily life. So, let us consider a circus in which in a particular act that are usually shown in circuses, that a particular performer, he supports the weights of 6 other performers, his co-performers in the group, and each of his co-performers are, say, so there are 6 co-performers in the group, each weighing 50 kgs, and one particular person is going to support their weight in a certain act, and consider G to be equal to 10 meter per second square, which you have seen that in many cases they are approximated, because 9.8 is a slightly odd number to calculate. So, the total weight of all those 6 performers put together is equal to total weight equal to 300 kgs. So, with G equal to 10, we get the total force that this particular performer will support is equal to 300 into 10, which is equal to 3000 newtons. All right. So, now this particular performer has got his femur bone, the bone in his legs. It's approximately, say for example, 0.5 meter long. So, femur bone of this equal to 0.5 meter long, and it's also equal to cross sectional area is 10 to the power minus 3 meters square. So, this is cross sectional area. We want to know how much of compression in his femur bones would cause for supporting 6 performers on top of him. So, consider the Young's modulus of the bone is approximately 10 to the power 10 Newton per meter square. Thus, what will happen is that it will cause an extension in his femur bone, which will go like which is equal to because he has 2 legs. So, this will be like 3000 divided by 2, which will get divided into 2 of his feet, and this will be like 0.5 meters divided by 10 to the power 10 Newton per meter square. This will be Newton here, and this will be like 10 to the power minus 3 meter square, and this will give us approximately a 10 to the power minus 6 meter. So, thus for supporting the weight of 6 performers, the extension or rather compression in his femur bone is of the order of 10 to the power 6 meters, which means like 1 micrometer, which is fairly small. So, we have talked about the compression on the bones of a performer in the circus. Now, let us take the same example, not with the bones of a human being, but rather with a steel wire, say. For example, so a steel wire, just for our convenience, the length which is same as the unstretched length, let us call that as simple as L, which is equal to 1 meter. Take that to be a thin wire, say the area of cross section to be 10 to the power minus 5 meters square, is subjected to a weight which is equal to, say for example, 500 kg. Do we really want 500 kg? Yes, maybe we want 500 kg. So, the force acting on the wire, so this mass is hung from a steel wire whose unstretched length L is equal to 1 meter. The area of cross section is 10 to the power minus 5 meters square, and there is a weight which is M is equal to 500 kg. Let us denote that by M, and hence the with G equal to 10 meters per second square, which is an approximate value which we often use, we can take this to be 5000 Newton. So, let us just try to calculate the extension of the steel wire due to this mass being hung at the bottom. Let us write down this formula, that y is equal to F over A n divided by delta L over L. So, you have a delta L over L equal to F by A y, and delta L becomes equal to F into L divided by A y. All the other quantities are given, and for a steel wire, y is equal to 2 into 10 to the power 11 Newton per meter square, and one can easily find out that this is equal to 2.5 millimeter. 2.5 millimeter of extension is actually detectable by the naked eye, and so you can see this extension of the rod. Now, we understand that why in this particular example we have taken a mass which is as large as 500 kg. Now, just to let you know that if it is a nylon wire, nylon has a Y which is approximately 50 times Young's modulus, 50 times lower than the value of steel, which means the extension for a nylon rod, for a nylon wire rather, is going to be 50 times more than 2.5 millimeter. So, this is a large extension which of course can be recorded. So, this distinguishes different materials undergoing different extensions under the application of a given force. So long we have talked about either compression of an object or extension of an object along one dimension or along one direction, so to say. Now, we can consider a different kind of deformation of an object, which is other than this simple extension or compression. So, which is for that, let us take this example of a thick book which is kept on. So, this is a side view of a book which is kept on a rough table, and if we want to consider that, so if we apply a force on the top of the book has an area of cross section to be A, so we apply a force on the top surface of the book which has an area of cross section A. There is a force that acts in the opposite direction which is of the same magnitude, and let us denote it by a negative sign, and this will cause an extension, let us call it as delta x here, and this is the original length L0. So, this resulting deformation of the book from its initial configuration as shown here is called as the shear, or this force per unit area is called as shearing stress.
As you see in this picture, there is a shearing stress being developed between two parts of the cube. They are sliding against each other. So, there is a shearing stress that is developed between the two parts.
Okay. And just a similar line of arguments will show that my so your F will still be proportional to delta x, which where delta x is indicated by this extension is proportional to the original length here, and it is also proportional to the area. So, combining just like before, if all these quantities we can write it is delta x by L0 into A, and similarly we can write that F equal to, or F over A is equal to G by delta x by L0. Just like the Young's modulus, G will be called as the shear modulus, and we are, and F over A as we said will be called as the shearing stress, delta x over L0 is called as the shearing strain. We can understand this shearing strain in a better manner if we draw a cylinder. So, this is my cylinder, this is my extension which is there, and there is a force which is acting this way, and equal force is acting on the other direction, and my this length is L. So, the shearing strain is given by delta x over L, or let us just put it as L naught as we have been doing, and this is given by tan of the angle of the deformation. Okay. And for this theta to be small, we can approximate sin tan theta as sin theta, because just to point out that tan theta equal to sin theta over cosine theta. So, as theta is small, sin theta will increase linearly as theta, whereas cosine theta will become equal to 1. So, tan theta becomes equal to sin theta, which becomes equal to, I am so sorry, this theta, and sin theta will be written as theta. So, so these are the shearing stress and the shearing strain relation, and this is very similar in not only in the looks, but also in form, excepting that you have not caused any extension or compression, but have simply given a shearing applied a shearing force, because of which this upright cylinder has become a cylinder which is inclined at an angle theta. So, the next thing that we are going to talk about is volume deformation. This is to say that it is not only in length or in area, we can also create a deformation to a particular object in all three possible directions, and by applying stress or applying a force which acts uniformly in all directions. A familiar example of this can be given for a body submerged in a liquid. So, this is a liquid, and let us take a body, just a cube in our case, and the forces acting are from all sides, and this will definitely create a compression in the system. And this since the force is acting perpendicular to this, we can replace the force by the area, and which is by the pressure due to the liquid. So, that tells you that in this particular case, it will cause a deformation to the body, where this pressure, let us call it a change in pressure compared to the original pressure, which is equal to which should be proportional to delta V over V 0, and hence this delta P, which is again the volume stress, can be written as B into delta V by V 0, where B is called as the bulk modulus. Of the system. So, this is and we have to put a negative sign here in accordance with the fact that as pressure increases, volume decreases. So, as you submerge this body deeper and deeper into the liquid, there will be increased pressure, and that will cause more the volume to compress more, and this is what the underwater divers do experience in their course of journey into the deep into the sea. And so, we have understood now there are three constants which adequately describe the mechanical properties of the body, which are Y as Young's modulus, G as shear modulus, and B as bulk modulus. So as you can see in this picture, cube is completely submerged in a liquid, so it's been acted upon by the force from all directions. And so there is on the right there is an underwater swimmer, and the forces are again exerted on him from all directions. So the bodies are undergoing volume deformation.
So now we are going to look at Hooke's law. This is named after Robert Hooke. From 1635 to 1703. So this is summarizing the findings that we have so far, and we can write for the first case of this tensile stress and the tensile strain, we had delta L over L0 connecting to F over A, and similarly the F over A is connected to delta X over L0, and finally this delta P, which is connected to the bulk modulus by delta V, and just in accordance with this L0 we will write a V0, which represents the original volume of the system. Now, as you can see that in this left hand side all these are stresses, and in the right hand side all these are strains. So there is a stress and this is strain, and in each one of them the stress is actually proportional to the strain, where the proportionality constants y, g and b are called as Young's modulus, shear modulus and the bulk modulus, which depend upon the properties of the material. And this is known as, this fact that stress is proportional to strain is known as Hooke's law. And so just to revise that, the stress has an unit of Pascal, which is equal to 1 Newton per meter square. So 1 Pascal equal to 1 Newton per meter square, and strain is of course dimensionless. And this brings us to the plot where we can plot stress versus strain in a generic manner, and we will get a straight line till certain values of stress, and after that this is going to have a non-linear behavior, and till this point till which the straight line behavior is obeyed, and that will be called as the, so this we will term as the elastic limit. So the significance of elastic limit is that the body will regain its original configuration once the force is removed, and beyond this the body is not going to regain its original configuration, because stress is no longer proportional to strain, and you will have a deformation here which is usually referred to as the plastic deformation.
The stress strain graph that we have talked about needs a little more closer look. If you look at the stress versus strain relationship, let us draw that again. Stress, which has the unit of pressure, which is like F over A, whereas strain
it's dimensionless, and this behaves like this initially, which is a straight line, which means that stress is proportional to strain, and in this regime all the way from this point O to the point A, Hooke's law is valid. So, stress is proportional to strain, and we know that the proportionality constant is called as the Young's modulus. Once you surpass this point A, which means the strain becomes larger than the value that is here, and you keep applying the stress via the weight or via the mass that was discussed earlier, this graph no longer remains a straight line as before, and it becomes like this, and it goes and it becomes like this. Let's discuss this region now. It is not a straight line, but it's fairly flat here between A and B, and which tells you that for a small increase in stress, the increase in strain is enormous. In other words, this region, in this particular region, the material has a plastic flow. So, it almost behaves like a fluid, and it flows and it reaches a point B. So, this region from B to C is quite interesting. It is interesting in the following sense, that there is a non-monotonicity at this point C. What I mean by non-monotonicity is the following, that as here, from here to here in this region, even though the stress is decreasing, the strain is increasing, which has not been the case so far. So, which means that even if it could happen that in a particular circumstances, the stress could actually decrease, however, the strain will continue increasing. There are specialized equipments where these kind of behavior can be detected, and this detection of this behavior can only happen close to the breaking point, and this D is called as the breaking point where the material breaks. So, this part between O and A is of importance to us, because this is where all our discussions are mostly concentrated to, because this is called as the elastic limit, or as I told earlier, Hooke's law is strictly valid, and beyond that Hooke's law begins to fail. So, before we end this class, let us take a look at what's going to be done in the next few classes, at least a couple of classes. So, we'll take a look at things such as different materials. So, different materials will be talked about, and maximum allowable loads. So that when construction takes place, we know exactly how much of load to put, such as the tensile stresses or the compressive stresses. So, these have to be known for different materials, especially the ones that are used in construction. Then we will take a look at experimental determination of Young's modulus.
Third, we will take a look at some of the technical definitions of certain terms which are used very often to discuss the elastic properties of matter, and they are so technical definition of say quantities such as called as toughness, brittleness, hardness, resilience, and stiffness. And finally, we will solve some problems these are the plans for the next class.